Hi, this is the Science Chef. In this video, we'll be looking at the valence shell electron-pair repulsion, also known as the VSEPR theory, and how it can be used to determine the shapes of molecules. Ensure you don't leave this channel, and we'll be right back in a jiffy. Glad to know that you are there. Molecular geometry is a three-dimensional arrangement of atoms in a molecule. Some properties of a molecule, such as its melting and boiling point, density, and the type of reactions it undergoes, depends on the molecule's geometry, which can be predicted to a reliable extent if the number of electrons surrounding its central atom in a Lewis structure is known. The theory behind this approach is the valence shell electron-pair repulsion theory, which works on the assumption that electron pairs in a valence shell of an atom repel one another. With the VSEPR model, we can predict the geometry of molecules and ions systematically. For convenience, we'll be dividing the molecules into two categories based on the central atom possessing lone pairs of electrons or not. Let's look at the first category: molecules with central atoms not having lone pair of electrons. You may need to watch our last tutorial video on covalent bonding and properties of covalent compounds to understand the difference between lone pairs and bonding pairs of electrons and how covalent bonds are formed. Just click on the link in the description to watch it. For convenience and better understanding, let's represent the molecules with a general molecular formula ABX, where A represents the central atom, B is the surrounding atoms, and X is the number of surrounding atoms present in the molecule and has integral values ranging from 2 to 6. For the purpose of this lesson, our focus shall be on molecules that have 2 to 4 surrounding atoms. Our first example is for molecules that fit the formula AB2, like carbon dioxide and beryllium chloride. In carbon dioxide, 2 oxygen atoms are doubly bonded to a central carbon atom, as shown in the Lewis structure. In the VSEPR model, double bonds and triple bonds are treated as single bonds, even though in reality they are larger than single bonds because of their higher electron density. Since the central carbon atom has no lone pair of electrons and the 2 carbon-oxygen double bonds are equal, the bonding pairs of electrons repel each other in a way that confers a high stability on the molecule, and that is the opposite sides of a straight line. Therefore, the shape of the carbon dioxide and similar molecules is predicted to be linear with a bond angle of 180 degrees, which is the sum of angles on a straight line. A bond angle is the angle between 2 adjacent bonds in a molecule. Next are molecules consisting of 3 surrounding atoms around the central atom. Examples are boron trifluoride and aluminum chloride. In boron trifluoride, 3 fluorine atoms are covalently bonded to a central boron atom, as represented in its Lewis structure. With the absence of a lone pair of electrons on the boron atom, the 3 bonding pairs of electrons repel themselves towards the corners of an equilateral triangle, with the boron atom at the center. This geometry, which provides a maximum stability to the molecule, is said to be trigonal planar, with a predicted bond angle of 120 degrees, obtained by dividing the angles at a point, that's 360 degrees, into 3. Our next example are molecules that contain 4 surrounding atoms and a central atom. Examples include methane and carbon tetrachloride. In a methane molecule, 4 hydrogen atoms are covalently bonded to a central carbon atom, and the repulsion from the 4 bonding pairs of electrons pushes the hydrogen atoms to the 4 corners of a tetrahedron for maximum stability, with the carbon atom at its center. Hence, the predicted shape of methane is tetrahedral with a bond angle of approximately 109.5 degrees. The second category are molecules with central atoms having 1 or more lone pairs of electrons. Let ABXEY be the general formula of such molecules, where A is the central atom, B the surrounding atom, E, the lone pairs of electrons on A. X and Y are integers with the values of X starting from 2 and Y starting from 1. Here, our focus shall be on the molecules that have not more than 3 surrounding atoms and not more than 2 lone pairs of electrons. It is important to note that, according to the VSEPR model, the order of repulsion of electron pairs around a central atom is strongest between lone pairs and weakest between bonding pairs. Our first example in this category will be molecules that consist of 2 surrounding atoms and 1 lone pair of electrons on their central atoms. Example is sulfur dioxide, SO2. From the Lewis structure of SO2, 2 oxygen atoms are doubly bonded to a central sulfur atom with a lone pair of electrons on the sulfur. Since the VSEPR treats double bonds as single bonds, the SO2 molecule can be viewed as consisting of 3 electron pairs on the sulfur atom. Of these, 2 are bonding pairs and 1 is a lone pair. Ordinarily, because of the 3 electron pairs, the overall arrangement is meant to be trigonal planar. But because one of the electron pairs is a lone pair, the SO2 molecule has a bent shape. Since the lone pair versus bonding pair repulsion is greater than the bonding pair versus bonding pair repulsion, the 2 sulfur-oxygen bonds are pushed together slightly and the oxygen-sulfur-oxygen angle is less than 120 degrees. Our next example are molecules that fit the formula AB3E with 3 surrounding atoms and a lone pair of electrons on their central atoms, of which ammonia is an example. In the ammonia molecule, 3 hydrogen atoms are singly bonded to a central nitrogen atom with a lone pair of electrons on the nitrogen atom. So, it contains 3 bonding pairs and a lone pair of electrons. Normally, the 4 pairs of electrons should confer a tetrahedral shape on the ammonia molecule. However, the presence of the lone pair repels the bonding pair and pushes them more closely together, and consequently, the hydrogen atoms are pushed towards the 3 corners of the triangular-based pyramid, with the nitrogen atom at its center and the lone pair of electrons at the apex of the pyramid. Therefore, the predicted geometry of the ammonia molecule is trigonal pyramidal with a bond angle of 107.3 degrees, which is smaller than the bond angle in a tetrahedron. The last example we shall be considering in this lesson are molecules that fit the general formula AB2E2. These molecules consist of 2 surrounding atoms and 2 lone pairs of electrons on the central atom. An example is the water molecule. In the water molecule, 2 hydrogen atoms are bonded to a central oxygen atom with 2 lone pairs of electrons on the oxygen atom. Like the methane molecule that is tetrahedral in shape, water has 4 electron pairs, but unlike methane, 2 of the 4 electron pairs are lone pairs. These lone pairs tend to repel themselves as far apart as possible for maximum stability of the molecule. Consequently, the 2 oxygen-hydrogen bonding pairs are pushed closer towards each other, and the predicted geometry of the water molecule is said to be bent or angular with a bond angle of about 104.5 degrees. In summary, the geometry of water shows a greater deviation from the tetrahedral angle than in ammonia. If you enjoyed this lesson, like, share this video, leave your comments and follow us on our social media platforms. Thanks for watching and always stay safe.